All right, everybody, welcome to our next talk in the workshop. And so this talk will be presented by Thomas Limbacher from TU Graz. Thomas, take it away.
So thanks. Yeah, so this talk is about a model for associative memory implemented by Hebbian plasticity. So why should we study Hebbian plasticity? Well, Hebbian plasticity is believed to play a central role in biological memory, and virtually any task faced by humans demands some form of memory. So, and while most models focus on working memory, many tasks require a memory mechanism that acts on a longer time scale, and often also require a more associative type of memory. For example, if we are introduced to someone and after some time we meet this person again and want to recall her or his name. And yeah, and today I'd like to present a spiking neural network model that is equipped with a hetero-associative memory that is subject to Hebbian plasticity. So here is a schematic of our model. It consists of standard live neurons simulated in discrete time. And at the core of our network model is a hetero-associative memory, which is a single-layer spiking neural network. And here, neurons set key in the key layer project to neurons set value in the value layer via these association synapses WASOC. And here we have the equation for the weight changes in the synapses. Here the Hebbian term strengthens the connections between coactive neurons in the key and value layer. Kappa here is just the exponential activity trace of these neurons. And the first term in the equation implements a soft upper bound on the weights. And the last term strengthens current associations and weakens old ones. So, and this simple hetero-associative memory architecture is motivated from the hippocampus, where rapid plasticity was found between area CA3 and CA1. In our model, the key layer would correspond to CA3 and the value layer to CA1. So, and only the association synapses are subject to Hebbian plasticity. The remaining weights in our model are trained using backpropagation through time. So how does it work? Our model takes a sequence of inputs. Here we have an example. In this example, we have sentences as input, which are Mary went to the bathroom, John moved to the hallway, and where is Mary? And each input can either be a fact or a query. In this example, x1 and x2 are facts, and x3 is a query to which the network should respond with an answer. And the inputs are encoded as a spike train by this input encoder here. And if the input is fact, then these neurons set S encoding are active, while neurons set R encoding are inactive. And these neurons set S encoding project to the key layer and to the value layer. And their activity will initiate a store operation. And if the input is a query, then neurons set R encoding are active, while neurons set S encoding are inactive. And these neurons here set R encoding project to the key layer, where their activity will initiate a recall operation. So for the first sentence in this example, the model could learn to associate Mary to bathroom. Here, the activity in the key layer would represent Mary, and similar, the bathroom would be represented by the activity of one or more neurons in the value layer. So in this sketch, this neuron is active for Mary, and this neuron is active for bathroom, and since they are co-active, the synaptic weight between these neurons is increased. And similar for the next sentence, the model could learn to associate John with hallway. So here we have the neuron representing John, and this neuron in the value layer represents hallway. And again, we have a weight increase between these neurons. And now for the query, the model could learn to use some representation of Mary to perform a memory recall. And ideally, the same neuron in the key layer that was previously active for input 1 for Mary should now be also active in this recall step. And since we have an increased synaptic weight between this neuron here and the neuron in the value layer, which was previously active for bathroom, this neuron can activate then this bathroom neuron here. And finally, the value layer projects to an output circuit, which then generates the final output of the model. So, and in some tasks, it can be beneficial to include information about the recalled value in the recall itself. And that's why we have included this feedback loop from the value layer to the key layer. And in this way, the recalled information can influence the recall itself after some feedback delay. Right, so in the first task, our model was required to store associations between random float vectors and integer labels. So in each instance of the task, we have generated n random float vectors and assigned an integer label to them. And these vector label pairs were sequentially presented as facts. After that, the network received a query vector, and the query vector was equal to one of the previously presented vectors. So in this example, vector is labeled 2. And the network had to output the label of the query vector. So here's the network activity for this example. But what we have found is that our model outperforms LSTM and LSN networks in this task. So here we have the test accuracy for various sequence length. So various vector label pairs, number of vector label pairs. And the accuracy of our model is above 90% for up to 50 vector label pairs, while the performance of the LSNN and LSTM quickly decreases with increasing sequence length. We've also found that our model shows superior generalization capabilities. So what we did here is we've trained the models with a sequence length of 5 vector label pairs and then tested with shorter and longer sequences. So, and while both models here, the LSTM and our model, in this case, generalized to shorter sequences, our model showed superior generalization to longer sequences. So in this next task, we applied our model to the problem of one-shot classification of the omniglot dataset. Here, we generated input sequences of omniglot, so images of omniglot classes. So we randomly sampled 5 omniglot classes and then generated this input. So each tuple here, or each pair in the sequence, contained one randomly sampled omniglot image of these 5 classes and a label from 1 to 5. And these image label pairs were presented to the network as facts. And then the network received a query image, and this query image showed another randomly sampled instance of one of these 5 omniglot classes. And the network had to output the label of this image. And this setup corresponds to one-shot 5-way classification. So for the omniglot images, we used the CNN as input encoder in this task. We have pre-trained the CNN with prototypical loss and then converted it to a spiking CNN by using the threshold balancing algorithm. So here is the TSNE visualization of the embeddings learned by the CNN. And we see there are only a few misclassified characters shown in red here. And overall, our model achieved an accuracy of 92.2% in this one-shot 5-way classification task of novel characters. I'm not aware of any spiking neural network model that was successfully applied to that task. So there is one model by Scher et al., and their spiking neural network model achieved 83.8%, but on a variant of this standard omnicloud task that we were considering. So in this task, the network was required to memorize associations between an audio input and an image. So here we again generated input sequences showing one audio sample from the free spoken digit data set and one MNIST image of the same digit. So we presented 3 pairs. And after that, the network received another audio query of one of those digits previously presented. And the task was to generate the MNIST image that was associated to the audio query. So to the same digit as the audio query. And we found that the reconstructed images are not just typical images for the digit class, but rather that they are pretty similar to the images that appeared with the audio cue. And overall, the mean squared difference between the reconstructed image and the target image was 0.03. So, and we next tested our model on the baby dataset. This dataset contains 20 different question answering tasks, and each task contains a sequence of statements followed by a question. And each of these tasks require different reasoning. So here we compare our model to the spiking relational network and to the HMEM model. So HMEM is a non-spiking memory network. And remember, we had this feedback loop in our model. And what we found is that our model struggled with some tasks. If we use direct feedback with a delay of 1 millisecond, and some tasks could be solved if we increase the feedback delay to 30 milliseconds. And overall, our model failed on 4 of 20 tasks in this baby dataset. And finally, we applied our model to an episodic reinforcement learning task. So here we used the popular children game Memory. It is played with a deck of n pairs of cards. And initially, the cards are shuffled and laid out face down. And a player has to flip over any 2 cards. And if they match, they are removed from the board. And the current player moves again. If they don't match, they are turned face down again, and the next player proceeds. And the player that collects more cards wins. So we consider a one-player version of this game, where the objective is simply to find all matching pairs with as few card flips as possible. And instead of using images, we use random vectors arranged on a one-dimensional grid of cells. And our agent was trained with proximal policy optimization. So here are example game moves for a game with 4 cards. And so in contrast to the other tasks we were considering, here where we always presented some facts followed by a query, here the agent had to figure out by itself when to store and recall information based only on the current observation vector. And the observation vector contains three components. So the state of cells, a state can either be empty, contain a face up or a face down card. Then the last action taken by the agent, and the face of the card the agent had turned in the previous time step. So we have tested our model with a game of 4 and 6 cards. So here in this figure in the middle, we see the number of flips required to finish a game over the number of games during training. And the figure on the right shows the histogram of card flips at test time for a random agent, our agent, and optimal agent. So for the 4-card game, we reached optimal performance. The 6-card game was a bit harder to train, but the agent still was close to optimal. So to conclude, our model integrates Hebbian plasticity in its network dynamics, and we found that this memory enrichment renders our model surprisingly flexible. So it endowed our model with the ability for out-of-distribution generalization, one-shot learning, cross-modal associations, language processing, and memory-dependent reward-based learning. So this suggests that Hebbian plasticity is a central component of information processing in the brain, but also in artificial spike-based computing systems. And since Hebbian plasticity can easily be implemented in hardware, this also suggests that powerful cognitive neuromorphic systems could be built based on this principle. So finally, I'd like to thank the Institute of Theoretical Computer Science based in Graz, Osan, and my supervisor, Robert Legenstein. And thank you for listening.
Thanks, Thomas, for that great talk. So we just have time for maybe 1 or 2 questions. So from the audience, is there anything that spiking buys you in this model, or is it mainly added for plausibility reasons?
It's mainly added for plausibility reasons, I would say. Yeah. I mean, yeah. Yeah, no, it's mainly for plausibility. So, yeah.
And to get just another quick question in, how relevant is the quality of the spike patterns for different inputs? Do they have to be clearly separable, or is there a winner-take-all mechanism implemented in the plasticity?
Yeah, so optimally, they should, I mean, the representation of the key and value should be orthogonal, right? So they should be clearly separable. Otherwise, it won't work. So this whole recall mechanism then, and also the associations. So, yeah.
All right. Well, thank you very much, Thomas, for your talk. And we will move on to the next contributed talk session. Thank you.